Hopefully you took the time to watch the short video about bunnies and dragons. And that is a really good explanation of the central limit theorem, which is super important. So I'm going to sort of go over it again to make sure that you really understand, because honestly, it's the most important theorem in statistics. It's how we will do everything from here on out in this course. So essentially what the central limit theorem tells us is that the larger the sample size, the sample mean or sample proportion, all of those samples of whatever sample size we get are approximately normal. So again, as n gets larger and larger, the sampling distribution becomes more and more normal. We will talk about those restrictions, but it's kind of crazy that if you have, say, a skewed or binomial or unimodal or whatever, everything ends up normal. So take a look. This obviously is a normal distribution. So what I'm graphing here, that I took a sample of 2 several times, and then I recorded the mean and then graphed those means here. If I have a sample size of 3, again, it already started as normal, so this one is still normal, but notice what's happening as sample size increases, it's getting skinnier and more normal. Now that's not super crazy when we're looking at the normal model, because of course the normal model will stay normal. But let's say this is the population distribution. So again, the population is uniform. And by that, I mean, for instance, if I were rolling a die, I would expect 1/6 of the time to get a 1, and 1/6 of the time to get a 2, and 1/6 of the time to get a 3, etc. That's a uniform distribution. If I start taking samples, however, and find the mean of every 2 rolls, notice it starts to look like the normal model. If I find the mean for every 5 rolls, notice now it's still the normal model, but the peak is a little bit higher and it's a little bit skinnier. And then of course, same thing happens here. It's more and more like the normal. And of course, the same thing would happen with the skewed population. As you can see, down with 5, we're almost to the normal. If I were to use 10, it would be normal. And so that's essentially what the central limit theorem is telling us, is that no matter what the population distribution looks like, the sampling distribution starts to look more and more normal. So again, know the difference between these two things. This is the actual population, like the 1/6 of the time I get a 1 and 1/6 I get a 2. This is the mean of samples of 2 or 5 or 10. So for any population of a large sample size, the sampling distribution of the sample mean, and it's going to be the same for a proportion, is approximately a normal distribution. Now this is going to be so important to us, and the reason that it's going to be important to us is because we know how to deal with the normal model. We know things that we can calculate, like a z-score, and that's what's going to end up happening throughout the rest of this course. Is we're going to be dealing with z-scores and t-scores that all have to do with the normal model or the student's t-model, which we'll learn in a few modules. So just a couple of pitfalls before we move forward and actually do some practice with this. And again, once we start to do some practice, it should make a little bit more sense to you if it's not quite coming together for you yet. But what we're basically saying is, for large sample sizes, the sampling distribution, which is the distribution of possible sample means or proportions from samples that size, will be approximately normal. So again, we're not talking about the population distribution, but the sample distribution. Sampling distributions arise because samples vary. So if you watch the bunnies video, each time he took a sample of different bunnies, you got a different mean of the weights of those bunnies, but overall, all of the samples together made that normal model. And the central limit theorem is essentially what's going to help us to do some calculations even when we don't know information about the population.